So we defined the notion of an inner product with the idea of getting hold of a definition of length of a vector v. So let's now begin by defining what is the length of a vector v in an inner product space v. So let v be an inner product space over f. For v in capital V, define the length of the vector v. It's denoted by length of v to be, we define it to be, the length of v is the square root of the inner product of v with itself. So notice that by positivity, irrespective of whether we consider a real vector space or a complex vector space, by positivity, inner product of v with itself is a positive real number. Hence, the length of v is a positive real number, which is just the square root of a positive real number. Let's look at an example. So, well, I don't want to spend too much time behind examples. You could go to each and every one of the examples of inner product spaces we have defined and take arbitrary elements and compute its length for getting used to this notion. So, in particular, if say 2, 3 belongs to R2, then what is going to be the length? Then the length in the standard inner product, the standard inner product was, recall that it was just the dot product, right? So this is just going to be norm of 2, 3, which will be equal to the square root of inner product of 2, 3 with itself, which is 2 square plus 3 square, which is equal to square root of 9 plus 4, 13. And how about the norm of the Pythagorean triplet 3, 4? You can check that this is just square root of 25, which is 5. But as you can see, this is with respect to the standard inner product. What if we change the inner product to the other inner product we were, so other inner product on R2 that we were considering. So let us consider length with respect to the inner product v comma w to be equal to 2 times v dot w. Let's see what happens here. Then what is the length of 2, 3, or let's not worry about 2, 3, let's worry about 3, 4. Let's put a prime here to denote that this is with respect to the non-standard inner product. So this is just going to be equal to square root of 2 times 25, which is equal to 5 root 2, which is not the same as the length that you obtain when you consider the length as defined using the standard inner product. So the length is a notion which very much depends on the inner product, and that is generally no standard notion of an inner product. So yes, so there is a notion of length which is very heavily dependent on the inner product. That is what you should keep in mind. Okay, so the positivity of the inner product tells us that the length of a non-zero vector cannot be 0. So let v be a non-zero vector. Then norm of v, which is equal to the square root of v comma v, Now, whatever is there inside the square root is a positive number, is not equal to 0. This is a positive number. So, hence, we have that we can conclude, in particular, norm of 0 is inner product of 0 with itself, which is equal to 0. And therefore, we can conclude that the length of any non-zero vector or any vector equal to 0 is if and only if v is equal to 0. In particular, the length is a positive number. Okay, let's conclude. Length of v is a non-negative real number with norm of v is equal to 0 if and only if v is the 0 vector. Okay, how about the length of a vector which has been dilated? So let's C be some scalar. So let C be in F. So as you can see, most of these conclusions are being drawn for vector spaces over F, or in other words, these are all conclusions which are true for both real vector spaces and complex vector spaces. So let C be in F and V be a vector in capital V. What is the length of C times V? The length of C times V is just square root of the inner product of CV with CV. But the linearity in the first property tells us that this is square root of C times V comma CV. And we have already checked in the last video that the conjugate linearity tells us that this is C bar V comma V, the inner product of V with itself. But what is inner product of V with itself? Inner product of V with itself is norm of V square. And what is the product of a complex number with its conjugate? It will just be the square of the absolute value. So this is just going to be square root of mod of C square times mod of V square, which is mod of C times norm of V. So in particular, if you look at minus of V, the length of minus of V will be the same as the length of V. Length of 3 plus 4i times V will be 5 times length of V, and so on. Alright, so we have now discussed how we can obtain the length of a vector from an inner product. In some cases, we could get hold of the inner product from the length of the vector. So let's see when that can be done. So consider the case. So let V be a vector in an inner product space and small w be equal to C times V, where C is a positive real number. It's a parallel vector in some sense. So it's in the same direction, it's just a dilation, positive real number. Let's see what happens to the inner product of V and W. We know that W is CV, so this is just V times CV. But what is CV? CV is, this is just C bar times V with inner product of V with itself. But C bar in our case is just C, and therefore because it's a real number, in fact it's a positive real number, this is just inner product of V with itself, which is equal to C times norm of V square. But what is norm of V square? This is just equal to norm of V times norm of CV by whatever we have just checked. Norm of, sorry, I am saying norm many times, but I mean length. The length of V times length of CV. But length of CV is just C times, or absolute value of C times the length of V, and absolute value of C here in this case is equal to C because C is a positive real number. And this is nothing but the length of V times the length of W. So, as noted, the inner product of V and W here in this case is just the product of the inner product of V and W. What if C is a negative real number? So, if C is a negative real number, let's not put it this way, let W be minus of CV, where C is a positive real number. That means it's a negative real number times V. C is a positive real number. Now what can we say about what is written above? Where does things start changing? It will be the same till, let me say that this is going to be the same till C times norm of V square minus of C times. This is just now going to be equal to minus of C times norm of V square, and it is at this place where it will change. This is just going to be minus of norm of V, or rather length of V times the length of CV, which is equal to minus of the length of V times the length of W, because absolute value of the negative of a number is so absolute value of minus C is just C, right? So this is precisely what we will be getting. So that means in this case the inner product is the minus of the length of V times the length of W. So in general, the inner product of V and W is always between these two numbers. So this is what is very famously called as the Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality. So it's a very celebrated result in mathematics. So let V be an inner product space. Over F. So we are not saying this just for vector spaces over R. This can be concluded for vector spaces over C as well. For V, W in capital V, we have the absolute value of the inner product of V comma W is less than or equal to the norm of, so the length of V times the length of W. So let's look at a proof of the statement. So how does the proof go? So if W is equal to 0, you can notice that both sides of the inequality will turn out to be 0, because the inner product of any vector with 0 is 0 and the length of the 0 vector is 0, as has already been noted. So if W is equal to 0, both sides above will be 0. There is nothing to prove, it is just equality then. So let us assume n is equal. So yes, in particular the inequality is satisfied. So assume that W is not equal to 0. We may assume without loss of generality that W is not equal to 0. The case when W equal to 0 has already been settled. Let's now invoke the positivity of the inner product on which vector? So consider, so let A and B be scalars. So let A comma B be in F scalars, B, and consider the vector AV plus BW. Now this is a vector in the vector space V, and by positivity of the inner product, so technically the third condition in the definition of an inner product, AV plus BW comma AV plus BW, the inner product of this vector with itself is greater than or equal to 0, with equality if the vector is 0. Let's see what is in the left hand side here. AV plus BW, if you look at the inner product of this with itself, by using the linearity, this is just A times the inner product of V with AV plus BW plus B times the inner product of W with AV plus BW. And pushing it more, this will just be equal to A bar inner product of V with itself plus B bar inner product of V with W plus BA bar inner product of W with V plus B bar inner product of W with itself. What is the product of a complex number with its conjugate? This is just mod A square. And how about inner product of V with itself? That's just the length of V with the product of the length of or rather the square of the length of V. And then this will be just AB bar VW plus BA bar WV plus mod B square, or rather length or mod B square times length of W square. This is precisely what we have, the inner product of AV plus BW with itself. Now this is true for any scalars A and B. So in particular, if we pick our scalars A and B carefully, we can say quite a lot of things about what we want to conclude. So pick A to be equal to mod W square, and let's see, B to be equal to minus of V comma W. So pick A and B to be these two scalars. Notice that A is going to be a positive real number and B is going to be some scalar in F. If it is a complex vector space, this could just be, might just turn out to be some complex number. So keep that in mind. And this hence will tell us that AV plus BW, the inner product of that with itself, is equal to the length of W to the power 4 times length of V square plus the length of W square times B bar. B bar is just minus of V comma W the whole bar, which is just so this is going to be minus, and this will be just the inner product of V with itself square. What is the next number? This is A bar. A bar is just A because A is a positive real number, and therefore this is plus length of W square times B is minus of VW. So let me change the sign here. So this is going to be minus of VW, and WV is just VW bar. So this is just again going to be inner product of VW square, mod of the absolute value of the inner product square, because we are multiplying a number with its conjugate. And how about the last term? The last term will be absolute value of B square. Absolute value of B square is just inner product of absolute value of inner product of V and W square, and this times norm of W square. And if you notice carefully, the last two terms can be cancelled out. And what remains is which is equal to norm of length of W square times length of W square times length of V square minus absolute value of inner product of V and W square. But by positivity, we have just observed a few minutes back that this is greater than or equal to 0, and the length of W is a positive quantity. Length of W square of the length of W is also a positive quantity, and therefore by multiplying by the reciprocal, we get mod of or absolute value of the inner product of V and W square is less than or equal to the length of V square times the length of W square. Now all these are positive numbers. By taking square root, we have the Cauchy-Schwarz inequality, which tells us that the absolute value of VW is less than or equal to the length of V times the length of W. And that's precisely what we were saying. If we look at W to be a positive multiple, scalar multiple of V, then this will be equal to the length of V times length of W. And otherwise it will be minus. If it is a negative multiple of V, then it's going to be a negative multiple, minus of length of V times length of W. And every other case will be between that. That's precisely what we have established. In the case of complex vector spaces, the Cauchy-Schwarz inequality tells us that the inner product of V and W, it lies in a disk centered at 0 and radius norm or length V times length W. That's precisely what the Cauchy-Schwarz inequality says for complex vector spaces. Right. So we have already noticed that the length is not a linear object. So we could consider the vector sum of two vectors and look at the length of that. This need not be equal to the sum of the length of these vectors. For example, as already noted, if you look at 1, 0, 0, 1, if you look at the sum, it's 1, 1, it has length root 2 with respect to the inner product obtained by the the length obtained by the standard inner product. And whereas 1, 0 and 0, 1 each has length 1. So we do not really get the length, sum of the length of these two vectors is 2, but the length of the sum of these two vectors is root 2. So we do not have linearity when it comes to length. However, we have a bound on the length of the sum, which is given by the very famous triangle inequality. So let's now prove what is classically known as the triangle inequality. So let V be an inner product space and suppose we take two vectors over F. So this is true for both real vector spaces and complex vector spaces. So let V comma W be two vectors in the inner product space V. Then the length of V plus W is bounded by the length of V plus the length of W. Let's give a proof of this statement. This is a very classical triangle inequality. It just tells us that the length of one side of a triangle, in the case of R2, this is effectively telling us that the length of one side of a triangle will always be less than or equal to the sum of the length of the other two sides of the triangle, and that is why it is called the triangle inequality. So in the case of R2, it manifests in that manner. So let's give a proof of this. It's actually quite remarkable that such an inequality is holding on any inner product space. So let us consider again positivity of the inner product with the vector V plus W. So we know that the inner product of V plus W with itself is greater than or equal to 0. But what is this? We know that this is inner product of V plus W with itself. This is just equal to inner product of V with itself plus inner product of V with W plus the inner product of W with V plus the inner product of W with itself. So what is this? This is just the length of V square plus the inner product of V comma W plus, what is inner product of W comma V? It's just inner product of V comma W conjugate plus the length of W square by the very definition of length. So what are we considering? This is inner product of V plus W. So what are we considering? We are just considering the inner product of V plus W with itself. So that is nothing but the length of V plus W the whole square, isn't it? So what is this? This is equal to the norm of V square plus 2 times the real part. So this is just A plus IB plus A minus IB, which is just going to be 2 times A, which is 2 times the real part of the inner product of V comma W plus norm of W square. If so, a check for you, an exercise for you is to check that, show that if Z is equal to A plus IB, then A is less than or equal to mod Z. This is something which you should be able to, yeah, because what is mod Z? Mod Z is square root of A square plus B square. Clearly it is greater than A. So something which you should sit down and think about, and with this you will be able to say that this is less than or equal to norm of V square plus 2 times the absolute value of the inner product of V with W plus the length of W square. But what do we know about the absolute value of the inner product of V and W? It has to be somewhere between 0, it will be in the disk with center at 0 and radius norm V or length V times length W. So this is less than or equal to, by Cauchy-Schwarz, 2 times the length of V plus the length of W plus the length of W square by Cauchy-Schwarz. Let me write just CS for Cauchy-Schwarz. And now the right hand side is just length of V plus length of W the whole square. So recall what we have done. We have just shown that, hence we have shown that norm of, or sorry, length of V plus W square is less than or equal to the length of V plus length of W whole square by taking square root, we have the length of V plus W is less than or equal to the length of V plus length of W, and that's precisely what we had intended to prove. So there are variants of the triangle inequality. So let me just leave it as an exercise for you to show that norm of, length of V minus W is greater than or equal to the length of V minus the length of W. So this is an exercise for you to work out. There are other variants which maybe we will see in the assignment. Okay, in the next video, we shall discuss the notion of the angle of a vector space, angle between two vectors, or, well, we might not see angle between two vectors. However, we will talk about orthogonality between two vectors. We'll try to capture when two vectors are in some sense perpendicular to each other in an inner product space.